Welcome everyone. Today we're diving into the fascinating world of projectile motion. Now, don't let the term intimidate you. Projectile motion is simply the motion of an object thrown or projected into the air, moving under the influence of a gravitational field. So let's break it down into simpler terms because I just want to introduce the concept to you in this video, and in the future we can go into situations where we're actually using kinematics to solve problems. Every projectile motion involves two main components. You've got a horizontal motion of component and you've got a vertical motion of component. The horizontal motion is constant, while the vertical motion is influenced by a gravitational field. Okay, so imagine you're tossing a ball horizontally. As we can see from this cannon on the top, I can see a horizontally fired ball that's coming out of that cannon. In the absence of air resistance, right? So the only force that's acting on that ball is the thrust that was provided by the explosion of the cannon, right? In the absence of air resistance, the ball would continually move horizontally at a constant velocity. However, we also have the gravitational field acting on the ball as well, resulting in force. F equals ma. In this case, that force being weight. So W equals mg. Just simply a contextualization of Newton's second F equals ma there, which is pulling it downwards, right? As we know that A is an acceleration, so we can say it is uniformly accelerating. Uniformly accelerating towards the ground. And as a consequence, the combination of that horizontal and that vertical downwards, we end up with the ball following a curved path, forming a parabola, right? This curved path there, referring to, you'll see it here in the diagram, scribbling on it, we can refer to as projectile motion. Now, what happens if we throw that ball at an angle? So before we had it being launched horizontally, and now we are projecting it upwards at an angle. We can see here angle theta. The motion is still a component, a combination, of those two components, the horizontal and the vertical component. The horizontal, right, as I'm circling here, is remaining constant. Just like before, if we're ignoring the frictional forces that are at play. But now we have a vertical component that we are first being provided by the launch of the projectile, because we launched it at an angle, which is going against initially the gravitational field. So we can see we start off with a large vertical component that came from the projection at an angle. We can see it decreases until it eventually reaches zero at the peak of this parabola here. Then there is no longer any of that vertical component acting upwards, and we just have the gravitational field continually pulling it downwards. Okay, so we end up with gravitation acting vertically, and we have our ball following this parabola, and the trajectory changes, right? So it starts going upwards, it reaches its peak, and it starts going downwards. Yeah, so I start with quite a large positive y component, eventually reaching zero, yeah, as it's being decelerated by the gravitational field, and then it becomes increasingly more negative as it is accelerated by the gravitational field, continues to be accelerated by the gravitational field. Now, depending what angle the ball is thrown at and the initial velocity it has, right? The combined, component of the two velocities here is being shown by these red arrows. I'm scribbling a lot here. But depending on that angle, initial angle, and that initial velocity, the trajectory changes, and it might go higher, it might go lower, it might go farther. All right. So let's have a look here. Let's have a look at these this graphical data from an experiment, which, I mean, you can try it yourself, just sort of, throwing at a constant velocity, right? You can sort of throw a ball from multiple angles, kind of see how far it goes. But we can see some sample results here from an experiment doing that on this graph. Y-axis representing the height that this projectile reaches, and the x-axis representing the x. So the y and the x both representing the y and the x components of displacement, yeah? Y displacement, x displacement. So we can observe how changing the angle and can affect the range and height of the projectile. Yeah, so this one that was launched at 75 degrees, it ends up going, incredibly high, and falling back down, but not traveling as far in the x. We can see that if you want distance, if you do want distance, and we can kind of show this mathematically using SUVAT in another video. If you do want x distance, the best thing you want to be doing is you want to be launching your projectile at 45 degrees. You will cover the most land in the x direction. So really, just to sum up today, projectile motion involves the motion of an object in 2 dimensions, horizontal and vertical. The vertical, of course, being influenced by the gravitational field, and the horizontal being affected by nothing if we're ignoring, frictional forces. Understanding these principles here will help us predict and analyze the motion of objects in various scenarios. So I hope this has either introduced or cleared up any pre-existing confusion about sort of the concept of projectile motion. Just remember that practice makes perfect. Keep experimenting, keep learning, and soon you'll be mastering projectile motion and other concepts like a pro. If you haven't already subscribed, I'd really appreciate it. Feel free to comment anything, any questions about this or any things you'd like to be covered. And if you look in the description or the about on the channel, I've got a link to a bunch of other socials and places where I post physics resources for those who are interested in lifelong learning of physics and mechanics. Thank you very much.